Hello and welcome everybody. It's my great pleasure to introduce Nathan Burrow, a fifth-year PhD student in computer science, and he's going to talk today about CFIXX Object Type Integrity. It's a novel mitigation that protects C++ applications against different forms of attacks and memory corruptions. I'm very interested in what he's going to say about it. Thank you.
Thank you, Matthias, for that introduction. So as mentioned, my name's Nathan Burrow, and I'm a fifth-year PhD student here at Purdue University. Today I will be presenting our work called CFIXX on object type integrity. As mentioned, it's a novel type of defense for preventing control flow hijacking attacks. So I'd like to start the talk with a brief survey. Who in this room uses a web browser? Everybody, right? Yep, get your hands up. Who uses Chrome, out of curiosity? And that leaves one person. What do you use?
Chrome.
Okay, so that's everyone uses Chrome. Lovely. So you may have heard of Google's pwn-to-own competitions and other bug bounty programs where they compete to have security researchers try to attack the browsers. So if you visit a website or accept network traffic of any kind through your browser, what can a malicious adversary achieve? And the answer is quite frequently that they can pop a shell, or in these competitions for humor, they pop things like calculators. So simply by using your browser to explore the web, you've potentially given a malicious actor a shell on your computer that they can then use to install their malware, read your files and exfiltrate them, or do whatever they want. So these browsers represent a significant code base that is network facing and frequently exploitable. So to give some more detail on how browsers are exploitable, need to introduce the idea of control flow hijacking attacks. So the idea here is that C and C++ programming languages are ubiquitously used. The browsers that we just mentioned are all primarily implemented in C++. The servers, which are listed here, are primarily implemented in C. And these languages provide neither memory nor type safety. So by sending the correctly formed input, the attacker is able to take control of these processes and cause them to execute a process of their choosing, aka a shell. So how big a problem is this in practice? Is this just an esoteric concern that no one really needs to worry about because it's so difficult, or is this widespread in practice? So we did a search of the CVEs and found that there were over 14,000 of them that gave the adversary code execution, and these are stats just for 2017. So yes, Matthias. Oh, what are CVEs? CVEs are common vulnerabilities and exploitations. So if you're a responsible security expert and you're doing analysis of some program and you find a bug and it's actually exploitable, you first report it to the vendor, and then when they fix it, you create a CVE and you report it publicly so that everyone knows what the problem was and that they should patch it. And these often come with proof of concept exploits, so that if you're a researcher and you're trying to duplicate it and see if some new defense policy would prevent this exploit, you have sort of the raw materials at hand to easily test that. And as we mentioned previously, these things allow attackers to control your systems and are generally bad. So for this audience, I'd like to talk a little bit about what is memory safety. I apologize for the quality of the next couple slides. These were sort of added in at the last second, so don't have lots of fancy animations and so forth. So you'll have to bear with me as I talk through these. So I mentioned that C and C++ are insecure because they don't provide memory or type safety. So first, what is memory safety? There are sort of two flavors of memory safety. So when you do a malloc, or you create an array on the stack, or even a local variable on the stack, these all create what you can think of as memory objects. They have a lifetime, either until you free them or until the stack frame returns. They have a size. They're either an array that's 10 entries long and each entry is 4 bytes, so it's really a 40-byte memory object. Or for malloc, you explicitly say how many bytes you want. So they have a fixed size and they have a fixed lifetime. So you can have two types of memory safety violations. You can have a spatial memory safety violation where the size property is violated. You have a pointer to this object and it's been incremented or decremented such that it no longer points to the object, but the memory either before or after it. As long as this is just a pointer, this is legal according to the C standard. Once you dereference that pointer and actually access the underlying memory and it's out of bounds for the object, you've committed a memory safety violation. So these have a couple of subtypes that you might think about. There could be sequential memory safety violations, which is your classic buffer overflow. You're reading input until you see a new line and you only allocated a 40 car long array, and the attacker sends you 200 bytes of data, and so suddenly bytes 41, 42, 43 start overwriting other things. You could also have an arbitrary violation. Let's say the attacker has overwritten a pointer on the stack or the heap or globally, wherever it is, and made it point to a location of their choosing. They now have an arbitrary memory write because the attacker is choosing the address that the pointer points to. And so by controlling the pointer, if it's then dereferenced, the attacker can control any location in memory without having to do a sequential write. So initial defenses like stack canaries that were aimed at buffer overflows on the stack and sequential writes are not powerful enough in general. There are also temporal memory safety issues. These are a little less easy to just talk track, but the sort of catchphrase here is use after free vulnerabilities or uninitialized reads. So by using these, the attacker can start modifying arbitrary memory, wherever that object was, and maybe a new object will get allocated there or already has been. So you can corrupt the internals of some other object using this old pointer. Type safety. Type safety, and again, this slide works much better with actual structs and memory regions and so forth, so I apologize. But there's sort of two different things you can do here. You can cast to a type that is larger than you are. So you have a 10-byte object, say, and you cast it to a type that's 20 bytes long. Well, suddenly you have access to an extra 10 bytes of memory that you weren't supposed to, and so you have a memory corruption through this. So in this way, type safety violations can lead to memory safety errors because you're accessing memory that you shouldn't be able to. There are also type confusion errors where you're misinterpreting the bytes. So let's say you have a struct that has a pointer field in it somewhere, and you have a struct of the same size that has a int field in it, and you cause a cast from the version with the pointer field to the version with the int field, and suddenly you're writing what you think is an int, but some other part of the program will come along and think it's a pointer, and suddenly the attacker's written an arbitrary pointer to memory and gains significant power from this. There are also variants of this that are C++ specific. So C++ really likes its class hierarchy. You can define a parent class and a child class, and maybe you don't just have one child, but you have a brother and a sister, and there's a whole family of them, so there's some cousin classes as well. And for polymorphism, we would like to be able to do upcasts. We want to take a child and cast it to the parent or the grandparent or what have you, and still be able to use it so that we can write detailed classes for very specific things, but then when we don't need the most specific thing, but just different abstraction over them, we can use the classes higher in the hierarchy. The problem comes in when you start doing downcasts. So every parent object is not necessarily a child, right? So if you have a child object and you've upcast it to parent, of course you can downcast it back to child. This is never going to cause problems because you're just returning to your original type. But if it was originally allocated as a parent and you're downcasting it to child, bad things can happen. The child might be bigger, you might be getting access to different memory. If you're corrupting the virtual table pointer to do this, you can start changing the actual virtual functions that get called. If the idea of a virtual table and a virtual table pointer and virtual functions are scary to you, worry not, I have slides. So before we get to them though, I want to talk a little bit about why C++ offers both unique vulnerabilities and chances for defenses to have traction. So, before we went into what is memory and type safety, we were worried about control flow hijacking attacks, which were giving the attackers the ability to hijack your process and execute whatever they wanted instead. So so they're using the memory and type safety vulnerability to achieve this, but their end goal is to change the control flow of the program by hijacking it. So to do this, they have to overwrite a code pointer somewhere in the program's memory. One of the classic targets is the return address on the stack. There are also, however, function pointers in C or these virtual table pointers in C++. So they're forward edges where there are variables that decide what function will get called. So you go through the program and, depending on its state in the execution path, you set this variable to some value, and then you call a function through that variable. So you're using, the C function pointer thing. And so the target is being determined at runtime based on some dynamic state. So it's very difficult to know at compile time, say, if you're emitting a defense, what is the correct target. And so it's protecting these forward edges that we're going to focus on here. We note that we can do a little bit better for C++, especially for virtual calls, because they have fairly strict semantics defined by the language. So in particular, a virtual call's target depends on the type of the object. So if you allocate a child object and you're going to call its foo method, you're always going to get the child's implementation of foo. You're not going to get the parents or the grandparents. Even if you happen to have cast the child object up and are treating it as a parent, you're always going to get the child's specific implementation of the virtual function. And this all depends on the allocated type of the function. However, once this gets compiled down to machine code, this distinction of what is the type of the object is no longer set in stone. It's reliant on a value that's just sitting there in the object's memory. So it can be corrupted through a memory or a type safety issue, and the type of the object changed. And then, the machine doesn't care. It's going to look at this, and if it points to an executable region of memory, it will happily try to execute them for you. So there's this semantic gap between what the language requires and what compilers currently emit in machine code, which does not enforce everything. So what we're going to do is we're going to fill this gap between the source level requirements and what actually happens in machine code. So I've mentioned the idea of virtual tables and virtual functions and virtual dispatch. So let's look at a code example to see how all this actually works in practice. So we're going to use this example several times, so it's worth going through it in a little bit of detail. So I've defined two classes. There's a class A, which has one member, which is just a string or a car star in this case. And then it has a virtual function. We don't really care what this function does. The point is that it's virtual, which means that classes that inherit from this class can redefine this to do something specific for them. So then we have a class B, which does inherit from class A, and as you might have suspected, does override the implementation of foo to do something specific to class B. And then let's see. What happens in this code, we have a main function that creates an object both of class A and of class B. So when you create the A object, it shows up on the heap, and it has two things in it. It has the pointer to the string that we would expect from the member, but the compiler secretly adds a hidden field to each polymorphic class, so any class that has a virtual function in it. And what this pointer does is it tells you where is the list of correct implementations of my virtual functions. So I have one virtual function foo, which implementation should I actually use? And this is stored in the virtual table. So all the virtual table is an array of function pointers for the correct implementation of each virtual function in the class. And so when you do this for B, you get a virtual table pointer to the virtual table for B, which has a function pointer to B's implementation of foo. So that when you come down here and we actually do virtual calls, so here I've defined a dispatch function, which takes one object. It's of class A, which means it can either be an A object or a B object that has been upcast to class A. And so we would expect this to call either the A implementation or the B implementation of foo, depending on the type of the underlying object. So at runtime, how is this type determined? Well, I'm missing some highlighting. The virtual table pointer field of the A object was supposed to turn green there, showing that it's been used to find the correct function pointer for the A foo. Similarly, when you do this for B, you come down here and you find the B implementation because the underlying type of the object was class B. So does everyone sort of understand how virtual dispatch and polymorphism are working? This is going to be key for the rest of the talk. If you're lost here, you might as well just take a nap. Okay, I'm going to... Well, so I was very tempted to say that Matthias was offering a all-expense-paid trip to the Bahamas for spring break for the person to ask the most interesting question, but then I'm not really that funny, so I didn't. Okay. So the question becomes, what can go wrong? We've seen how dynamic dispatch works, so now we need to consider how an attacker might go about abusing it. So here, it's the same program that we've seen before, except that we've added in an arbitrary right for the attacker in a vulnerable function. We don't really care how this function is implemented, just that it gives the attacker an arbitrary right. So what might the attacker do with this? Well, the virtual table pointer is determining at runtime what function is getting called. So maybe the attacker would like a different implementation of the foo function to be called. And so they could redirect the virtual table pointer to point to the B implementation, even though this was an A object. And similarly, just for a nice illustration, they could overwrite the other virtual table pointer in the B object to point to the A implementation. So now when we come down here and do dispatch, oh no, this was allocated as an A object, but we're getting the B implementation of the foo function. This may not seem serious. It may sort of seem like a parlor trick or just sort of a prank that you can play, but there's been work to show that this actually gives arbitrary execution in practice and is enough, with sufficient, analysis to string these together to actually get a shell out of it. And so the more powerful version of this is, what if we don't just change to an existing virtual table? What if we wanted to inject an entirely new synthetic object and completely blow away the object to be something of our choosing? What could we do? Well, again, we have the arbitrary right through the vulnerable function, but here the attacker could just completely wipe out and replace the memory contents of these objects. And the virtual table pointer will still be there, but the virtual table doesn't necessarily have to be an existing one for a programmer-defined class. It just needs to be an array of function pointers with a pointer to the function the attacker cares about at the right index. So the attacker could add in the address of, say, system if they happen to know what it is. And then when you come to the dispatch, oh no, we're calling system. And I don't have an animation for that, but I think we've all seen this example enough to follow along. So synthetic objects were first proposed in a paper called Counterfeit Object-Oriented Programming. I like to pronounce the acronym COOP, that was presented at Oakland in 2015. So this is a fairly cool attack paper, and if you're into how can you do fancy forms of control flow hijacking for C++, I recommend you go read it. Okay, so people have known about these attacks for a while. This is not new news, so to speak. So what has the research community attempted to do about it? The current state-of-the-art defense is known as control flow integrity. The idea of this defense is for each indirect call site, so everywhere a function pointer is going to be used or virtual dispatch is going to be happened, we're going to look at all the functions in the program and try to figure out which ones could possibly have the programmer meant to call here. So in general, this means we look at the function prototype. Okay, this is a function that returns an int. It has 3 arguments. The arguments are of type, char, int, and float. So we're going to find every address taken function that returns an int and has 3 arguments of those types. And we're going to say that you're allowed to call those here. This is, of course, hugely over-approximate, but it's static analysis, so there are some limits to what you can do because of alias analysis. So if at any point you cast a function pointer to, say, a void star, which is an unfortunately common paradigm, and then you cast it back to this, suddenly it's very hard for a static analysis to figure out what are the set of things it actually was intended to point to. Because void star could point to anything, and if there are other assignments to this, and so forth. So it's in general undecidable. There have been papers that try to do better than just all functions with the correct prototype, and they can get some traction in some cases, but in general, they still have to fall back to everything with the right prototype. So the big weakness of this is that it's using static analysis and over-approximate, that it's limiting the attacker to a set of allowed functions. And so it's likely, although not been demonstrated, that just by bending, I misspoke. It has been demonstrated that just by bending control flow within the allowed set for any possible CFI implementation, you can achieve arbitrary execution in some cases. This was the control flow bending paper. But it has some advantages too, because it's making life significantly harder. So instead of at these indirect call sites being able to go to any executable byte in the program, you're now limited to a set of functions. So fancy attacks that look for 4 and 5 byte long so-called gadgets like ROP have been significantly mitigated, because now you have to use entire functions. So that helps. And it comes with low overhead. You're doing all your analysis at compile time. No one really cares if it takes longer to compile your program. They care about the actual execution time, the runtime overhead of it. And these have been significantly optimized through 10 years of research to be about 2% overhead for the best implementations. So these are cheap and they are providing power. They just aren't quite good enough, as we will show. So to make this a little more concrete, we have a nice little animation here. We have a call through a function pointer, and there are these arrows to say, oh, look, it could point anywhere in memory. And now we add in CFI, and some of the arrows have been blocked out, which I denote by turning them red, and you're down to a set of allowed targets. So is CFI making sense to everyone? Okay. So now we finally get to talk about the new fun stuff that I've done, namely object type integrity. So OTI is a new class of defense policies for C++. The main thing here is that we're not going to protect call sites. We're going to protect the objects themselves. And in particular, when you had this object on the heap in its virtual table, we're going to put a lock on this relationship. We're not going to let the attacker choose the virtual table that's associated with an object. Another way of saying this is that the attacker cannot control the type of the object. I'm going to wander back behind here. Right. So there are a couple other things that are worth noting here. OTI requires the objects to have a known type. So if you're doing the synthetic object type attack and just completely injecting your own object, that object will not have a known type per the OTI policy. So we're going to detect that as well. We are the first defense to do so in a truly principled manner. Further, this policy is extensible. I'm going to be talking today about how it can be used to protect dynamic cast, but it could also be used for type safety and possibly even use after free protection. So back to our little graphic that we use for CFI. So whereas CFI limited it to a set of targets, OTI is going to limit it to a single target at runtime. Because the type of the object uniquely determines the virtual function that should be called at a virtual dispatch site, by guaranteeing the type associated with an object, when you do dispatch on this object, you're always going to get the single correct target. So we no longer have an approximation problem. So to show that this is not just some ivory tower idea and that it actually works in practice, we were obligated to come up with a prototype. This is why grad students exist. Professors exist to have fun ideas. Grad students exist to prove that they work in practice. So we call this prototype implementation CFIXX. And what it does is it enforces the C++ object type semantics at the machine level. So it does what you would expect from this talk. We've looked at the type according to the C++ semantics, and we're going to inject some code to ensure that that type cannot be modified, and so that these semantics are actually enforced at the machine level. To do this, we have to instrument a couple of things. We have to instrument objects constructors so that we can record their types. And we also have to instrument dynamic dispatch to enforce our actual policy. So once we have the type of the object at a dispatch site, what are we going to do? There are two options. You could just prevent any attack from happening. You could use our protected type and ignore the vulnerable type in the object and know that the correct virtual function is always going to be called. But maybe you don't just want to guarantee that the correct virtual function will be called. Perhaps you're willing to pay a little extra overhead and actually detect that an attack is happening. In this case, you can compare the type stored in the object to our protected type, and if they differ, you can detect an attack or a bug or what have you, depending on your context. So for this talk, we're going to focus on the idea of prevention. Okay, so how is CFIXX designed? It's a compile time instrumentation. It's implemented on top of LLVM 3.9.1. It comes in two parts, as I mentioned. We have to know the correct type of the object. This is determined in the object's constructor. So we instrument the constructors to record the correct type for the objects. And then we use these types for dynamic dispatch, and there will be an illustration of how all this works out coming up. We do require a runtime library, which is just a memory mapped region of memory that we use to score the correct types in. So how does this work in practice? Okay, so here we're allocating our A object as usual for our little code example. And then we come along and it's actually being created on the heap. So previously you have the virtual table pointer that only pointed to the virtual table. What we've done is we've added in a metadata table. We're using the address of A as the index into this table and storing the correct virtual table pointer for A at the slot indicated by its address. Right? So in addition to having the type stored in the object, we now also have it replicated in our metadata table. Similarly for B, we do the same thing. So now when you come to dynamic dispatch, you use the virtual table pointer or type for the object that was stored in our protected region. So even if an attacker has changed the virtual table pointer in the object, it doesn't matter because we're using our protected one, so the correct function will still be called. Okay, so to show how this might work versus an attack, here we actually have a little animation to show that the virtual table pointer in the object has been corrupted, but now we come to the dispatch and we're using the correct one. So this is just some animation in color to show what I explained to you previously. Yep, is this clear to everyone? The attacker has corrupted the type in the actual object, but it doesn't matter because the attacker can't change where the object was allocated, so we can look up the correct type for that object and use it to make sure that the correct virtual function gets called. So it's nicely simple and elegant in practice. All right, but all this would be worthless if the attacker can just come along and modify our metadata instead of modifying the type in the object, right? So I have to be able to convince you and the security community in general that our metadata is actually integrity protected, that only our instrumentation can write to it and not an attacker. So as you might suspect, we have two classes of writes in the program. There are those that we have inserted through our instrumentation that are actually allowed to access the metadata, and there are all other writes. So all the other writes should not be able to access the metadata. And so you can think of this as saying that they must be in bounds for the rest of memory. So you can think of this as being an array bounds check. That there are two areas of memory. There's the region that most writes are allowed to write to, and then there's our specific metadata region. And so this brought to mind Intel's new memory protection extensions. This is an ISA feature that lets you do array bounds checks very quickly. Once you have the bounds loaded in their special bounds register, it becomes one instruction and the hardware does the comparison and generates a signal if it has failed. There is one catch, however, in that you need one contiguous region of memory to check with MPX. It doesn't like you saying inbounds are from 0 to 50 and then from 70 to 100 also. It wants one region of memory. So to do this, what we've done is we perform our checks on a rotated address space. We calculate how much we have to add so that our metadata table is at the top of the address space instead of being wherever it is in the middle. And then, because of integer overflow, you add that much, and the rotation, as shown sort of on the right side of this figure, happens. So now you have our metadata table on the top of this rotated address space, and you can use one MPX instruction to ask, is the rotated pointer below the metadata table or not? So this is a new application of MPX, and it's kind of fun because this issue comes up fairly often for runtime defenses, that they want to have some sort of metadata or information about the program state on the side that they're going to look at to decide how to enforce their defense policies. So this, it's both an engineering detail and a design decision because it's how can we take this and make it fit what we need. So does anyone have any questions about this as I take a drink? Okay, cool. This is just one detail that I'm particularly proud of. even though it's perhaps less important to the overall work, which is mainly focused on the control flow hijacking and how to secure the virtual calls. Since I have 50 minutes instead of 20, I've decided to bore you with details about how this metadata table is actually implemented. It doesn't particularly matter, but it's a 2-level page table. So you have a pointer as shown here in this bar on the bottom. And so you have a top-level page table and then various second-level page tables. So you look at the top 22 bits of the pointer and you use them as an index in the top-level table. That gets you a pointer to the relevant second-level table where you use the next 20 bits as the index into that. And so that's how you convert the address of the object into an actual metadata entry. You do the usual page table walk where this is how we've split it up and structured it. The details here are really not important. I just thought I would mention them as a time filler. Okay. So everyone took a nap for that slide, right? Yep. Okay, good. All right. So we've talked, whoops. Shouldn't rest my finger on my clicker. We've talked a lot about the theory of all this, but we do have to show that it works in practice. And so to do an evaluation, I'm going to talk to you both about how we've quantitatively evaluated the security of this project and how it can be combined with control flow integrity, which was the existing technique and the benefits you might get from doing that. And then we also have a performance evaluation. Noticeably, we were able to compile more than just toy benchmarks. So we actually got Chrome to compile and ran the standard JavaScript benchmarks with about 2% overhead. We also ran the usual compiler suite of benchmarks, which is known as SPEC CPU. Okay, so for security, how do existing defenses work? These are all just CFI implementations. So they're based on static analysis. And so at the dispatch site, if you were just looking at any address taken function, the green circles show the functions that you might target. When you apply LLVM CFI, it's aware of the class hierarchy. So because this is an A object that's being used, it's able to limit it to just the 2 functions in that class hierarchy. vTrust is a less general policy. It's only focused on C++, whereas LLVM CFI also protects C-style indirect pointers, C-style function pointers. And it also leverages a class hierarchy analysis and achieves basically the same precision. CPS is a policy that achieves better precision. What CPS can be thought of as a subset of memory safety. So they say we're going to protect all code pointers. We're going to move them to a separate region of memory, and there aren't going to be any arrays or anything there, so that attacker cannot easily corrupt them. There are, of course, some ifs, ands, and buts, and there's a heavier weight policy known as CFI that addresses many of those. But CPS is the one that achieves roughly comparable performance, so it's the policy we'll look at. And because it's actually integrity protecting the pointer, sort of, it can detect that there should only be one valid target based on the object. Okay. So to show the differences and sort of tease out the different issues in these policies, we've created some microbenchmarks, which just show different attacks, and then we compiled them with the various defenses and saw what targets we were actually able to address. So the first one is fake virtual tables, where you inject a virtual table of your choosing, and all the defenses are able to do with that. If you do a slightly fancier version of this, where you actually make sure that the function prototypes in your injected virtual table match up, they're all still able to deal with that. Virtual table exchange is like what I showed you on one of those first slides, where we crossed the virtual table pointers and pointed it to something different. That's also handled by existing defenses. Where existing defenses struggle is if you change the virtual table to be that of a related class. They can't detect that because they're statically allowing the entire class hierarchy, so you can get away with violating them. And then when you do COOP-style synthetic objects, CPS is not able to deal with this because they don't know what the correct type of the object should have been. Even though they're protecting the virtual table pointer, they don't know what its correct value was, and they aren't tracing it throughout the lifetime of the object, so they aren't able to detect these attacks. Okay, so in a nutshell, OTI versus CFI. So object type integrity can be combined with control flow integrity. It's fairly apparent why this is so. Control flow integrity is focusing on call sites. We're focusing on objects. So there's no reason that these policies should conflict. As I've mentioned, control flow integrity is over approximate, but what it does get you is that there's an absolute set of allowed targets for a call site. So with ours, we're guaranteeing the correctness of virtual dispatch for a given object. However, if an attacker is able to modify the data flow through the program such that the wrong object reaches a virtual dispatch site, we can't detect that. We will make sure that the correct virtual function is called, but if it's the wrong object, well, we're going to get the wrong virtual function. So if you add in CFI, you can limit the set of objects that an attacker can substitute to ones that would be, at least in the same class hierarchy. So this provides a little bit of extra defense there. And just from an engineering perspective, I was shocked. I just used our modified Clang and turned on the CFI flag, and all the benchmarks still worked. This was unheard of. It made my life super easy. I thought I was going to have to spend a month debugging. But sort of the larger design level point is that these are truly compatible policies that aren't conflicting. They're addressing different parts of the program. Okay, so performance results time. So on the x-axis, you can see the 7 C++ spec benchmarks. We got all of them to run, and which is not necessarily a case for compiler-based defenses. There's often one or two missing for engineering reasons. And then on the y-axis is the percent overhead. So we're showing two different results here. The lighter bar is just the overhead from switching to the CFIXX dispatch scheme. So for creating the metadata table and maintaining entries in it, and then using our protected types for virtual dispatch instead of using the one in the object. So for just doing all of that, we get about 2% overhead. Then when you add in MPX and start integrity protecting the metadata table, because you're checking every write in the program, there's of course slightly more overhead. We end up at 5% on average, although you can see that there's that one pathological case for Omnet that ends up at 13% or so. So, you get what you pay for. So in conclusion, object type integrity is a new class of defense policy. We've shown how it can be used to protect virtual dispatch, but because we're tracking types of objects, it's clearly extensible to type safety issues. And because we're maintaining metadata per object, there are also some interesting applications to use after free protection. It has low performance overhead, 2% on Chrome, and within the same ballpark on the computation-intensive SPEC CPU benchmarks. We've shown how it can be combined with control flow integrity to mitigate data flow attacks. And our implementation is open source at this link. I encourage you to go check it out. And with that, I am done, and I'm happy to take any questions.
Questions?
Sounds like good computer science. I have questions now. This might be a dumb question.
No dumb questions.
So how do the hackers redirect the pointer to another function? Like we have two functions, like the full function in object A and full function in object B. So how do the hackers redirect the pointer to the full function in object A to that one in object B?
Yeah, so that's a good question. The naive way that they might try to do it is to edit the actual virtual tables and change the function pointer that's stored there. Unfortunately for attackers, these are statically determined at runtime, so we can map them into read-only memory. So you can't directly modify the virtual tables. What you can do is change the pointer to these tables, right? So virtual calls are double indirect. You go through the pointer to the virtual table to find the pointer to the function that you want to call. So you've traversed two pointers. And the second one is secure because it's read-only. The first one, however, is in writable memory, because for each object that you allocate, you have to be able to write into it, okay, what is the correct virtual table for this? And so because that virtual table pointer's sitting there in writable memory, the attacker can use the underlying bug of their choice. We don't care. It's probably going to be a memory or a type safety issue. And use that to overwrite the virtual table pointer. And then, to choose their function, they just have to choose what virtual table they point to, or maybe they don't point to the beginning of a virtual table. Maybe they point 4 entries above it so that when they use the index, they end up at the function of their choosing, even if it wasn't at the correct index to begin with.
Any other questions? Let's thank Jason again.
Thank you.